So in the previous slide, we defined what is the transverse wave. Now let's try to study the second kind of category, which is the longitudinal wave. So what is the longitudinal wave? It is also a wave, and now the wave propagation is still to the right. But now the media or the particles is oscillate in the same directions of the wave propagation, but once again the medium do not move with respect to the wave. So you can see they just oscillate locally back and forth, parallel to the direction of wave propagation. So it is a compression and rarefaction of the medium, and now because of this oscillation, the longitudinal wave is propagated. However, the definition of the wavelength is still the same. So this is the so-called wavelength. It is the point that repeat themselves. So that is what we mean by the longitudinal wave. So now let's take a look about this slide again. So two types of the wave. They differ because the directions in which the medium vibrate. So if the medium vibrate is up and down perpendicular to the wave propagation, then it is the transverse wave. But if the vibration of the media is parallel to the direction of wave propagation, it is longitudinal one. So you can see now that's the reason I show you two figures, and this is the transverse wave and this is the longitudinal wave. So now let's have our second conceptual quiz today. So the vibration along the transverse wave move in a direction. The answer is B, because now it is a transverse wave, yeah? So the vibration of the medium itself should be perpendicular to the direction of wave propagation. So if I change the question now to the longitudinal one, then the answer should be A, yeah? So you should not try to remember the answer, but try to remember how we define the wave. Now let's have one more conceptual quiz. So when you go to the football game or baseball game, people will do the wave, yeah? And what people do the wave is that, how they do it is that the audience will stand up and down, and you can see that it seems they produce a wave propagate along the stadium. So in this kind of wave motions, people stand up and down. What type of wave it is? So I think now it is a trivial answer to you. It should be a transverse, yeah? Because now you can use the people's motion as to visualize them as a movement, that vibration of the medium. And you as a particle, you are not leaving your seat, yeah? You are staying at your original position. But what you are doing is you are just oscillate locally up and down. But the wave is propagated perpendicular to the direction of your vibrations. So the answer is B. So now we define there are two categories of the wave. But in the nature, the thing is not easy. So I'm going to give you the first example of the wave in the nature. It is the water wave. So if you throw a stone into the pump, so they will hit the surface, and you will find out that there will be a wave propagate outward spherically. So apparently it is a wave, yeah? Because you can define what is the wavelength, and you can also define the period and define the frequency. So basically the behavior itself is just a wave. However, the water wave is not simply a transverse wave or a pure longitudinal wave. It is a combination of two. So let's try to take a look about the figure on the right hand side here carefully. So this is the surface of the water. So it is not a flat surface. So that when water wave propagate along to this direction, dashed line here, let's put the particles here to visualize the motion of the water molecules. So you will find out these particles, when the wave propagate, they will shift a little bit to the right. But now they will go downward, now shift a little bit to the left, and going back. So you can see this motion is actually a combination of the transverse and the longitudinal one. So which means the motion of the medium is simultaneously perpendicular and parallel to the direction of wave propagation. And that is the sound wave. So don't simply say the water wave is a transverse or longitudinal wave. The second example is the sound wave. So when you hear what I'm saying now, basically we are communicate with each other through the sound wave. So we claim that the sound wave is a longitudinal wave, which means the vibration of the medium is parallel to the direction of wave propagation. And now the medium we are talking about is air molecule. So what will happen is this. So these tiny particles are the air molecules. So when you compress the air around, or when you speak, let me say this way, you try to compress the particles around the speaker here. So when you compress here, you create a bigger pressure, yeah? And now you have fewer particles here. So the pressure here is lower. So when you're speaking, actually you create a pressure difference. And when the pressure was passed through along the material, you can see that the particles still stay originally, but they are oscillated along left and right directions. And it is the wave, the pressure was transmitted. And now the pressure of the air molecules will hit on the eardrum of your ear, and they will vibrate the eardrum, so you can hear my voice. So you can also use the spring to visualize the same process. When you oscillate the spring, it is exactly the same thing. You try to compress them, and now this compression will be transmitted along the spring. However, the spring itself is not moving. And the second thing is that how fast does the sound propagate? So if the sound travels in the air at a temperature 20 Celsius, then the speed of the sound wave is 340 meters per second. So there are two important things you should pay attention. The first is which kind of medium it is. Now I'm talking about in the air. The second thing is the temperatures. So in the chapter 6 and 7, you know that the temperature is related to the kinetic energy of the particles. So apparently, the higher the temperature, the faster the air molecule is moving. So this one also will play a very crucial role to determine how fast the sound wave propagate in the space. So now, let me give you more details about how you hear a voice from the loudspeaker. So for example, you can image that the loudspeaker is a paper cone, and you can try to vibrate. So when the paper cone vibrates, the air molecule next to the loudspeaker will start to vibrate, because thinking about that, they have the physical contact with each other. Yeah? So when the paper cone try to vibrate, they will try to push on the air particle around the paper cone. So now they will start to compress and or do the rarefaction for the air molecules. So they will start to vibrate, and this vibration of the air molecules will be transmitted. And now they will reach to your ears and set the same kind of vibration to your eardrum. So therefore, in the sound wave, the most important quantity is two different kind of quantities. The first is the density, and the second one is the pressure of the air. You can see that the propagation of the sound wave is due to the oscillation of the air molecules. So when they oscillate or vibrate locally, you create a density difference. And this vibration of the density difference will cause the oscillation of the pressure. Yeah? Because now you have higher pressure here and lower pressure here. So now let's take a look about this diagram. Here, the y-axis is the density vibration, and the x-axis value is the direction of propagation. So you can see the density vibration is biggest in these regions. and is smallest in these regions. And simultaneously, because the density here is higher, they will create a higher pressure here. And for this point, you create a lower pressure here. And from the fluid set chapters, chapter 5, we have learned that if you have a pressure difference, you will create a force. Do you still remember the Bernoulli's principles? So the Bernoulli principles say that if you create a pressure difference in the lower and upper surface of the airplane, the air wing, you will create an upward force. So the difference of the pressure acting on the surface actually create a force. So therefore now, the wave will have a tendency to move from the higher pressure to a lower pressure, and then they will propagate through the space in the positive x directions. So it is, for the sound wave, actually it is the vibration of the density. You can consider it is a particle, and then the vibration of the particle will cause the pressure difference. But however, like all the other waves, only the energy was carried away eventually. So the hertz is the SI unit for the wave, for the frequency. So no matter what kind of wave, you can use the hertz to describe the frequency. So for our human ear, the range of the frequency you can hear is from between the 20 hertz up to 20,000 hertz. So if it is the sound wave above the 20,000 hertz, it is called ultrasonic. So often also, the animals in the ocean, they will try to communicate with each other using this high frequency sound wave to each other. You cannot hear that, but they can hear each other. And the frequency less than 20 hertz is the infrasonic one. So this just give a sense of feeling. Ultrasonic, which means it is a frequency beyond our highest tolerance. And now for the infrasonic, it is the frequency very low, which is even below the minimum frequency that our ear can hear.